Nobody told you what Voyager 2 actually found. They gave you the headlines. They gave you the press releases. They told you it was a triumph of human engineering. And all of that is true. But the real story, the one buried under decades of scientific jargon and carefully managed announcements, is something far more unsettling. Because what Voyager 2 discovered at the edge of our solar system did not confirm what scientists expected. It shattered it. And right now, as you read this, the spacecraft is going dark, one instrument at a time, like a soldier taking its final breaths on a battlefield nobody else has ever reached. What did it find out there, and why does it matter more today than ever before? There's a spacecraft hurtling through the void right now, more than 13 billion miles from Earth, running on power equivalent to a dim refrigerator light bulb, and it is still sending data home. Think about that for a moment. 13 billion miles. A signal traveling at the speed of light takes over 19 hours just to reach us from where Voyager 2 currently is. By the time you finish watching a movie tonight, that signal will still be in transit. And yet, NASA engineers sit at their consoles, waiting, listening, translating the faintest electronic whispers into scientific revelation. Voyager 2 launched on August 20th, 1977, a time when the Soviet Union still existed, when personal computers had not yet reached the public, when the idea of sending a machine to the stars was considered the wild ambition of dreamers. And yet, here we are, nearly 5 decades later, and that machine is still out there, still functioning, still teaching us things we did not know. The question is, what exactly has it been teaching us? And more importantly, what has it found that we are only now beginning to understand? This is not a story about nostalgia. This is not a celebration of vintage technology. This is a story about what lies beyond the boundary of everything we call home, and the deeply unsettling reality that the universe out there does not behave the way our best models predicted it would. To understand what Voyager 2 found, you first need to understand what it passed through to get there. Our solar system is not simply a collection of planets floating in empty space. It exists inside a bubble, a vast magnetic envelope generated by the sun, stretching billions of miles in every direction, filled with charged particles and solar wind and magnetic fields that define a kind of cosmic territory. Scientists call this bubble the heliosphere. For most of human history, nobody knew where it ended. Nobody knew what was on the other side. And the truth is, for most of human history, nobody had the means to find out. Voyager 2 changed that. But here is where it gets interesting. Because Voyager 2 did not simply fly out and confirm what scientists had predicted. What it encountered at the edge of that bubble was something that contradicted decades of theoretical models in ways that researchers are still working to reconcile today. On November 5th, 2018, Voyager 2 crossed into interstellar space, the region between the stars. It became only the second spacecraft in history to enter interstellar space while continuing to transmit scientific data directly back to Earth. Its twin, Voyager 1, had crossed this threshold 6 years earlier in 2012. But there was a critical difference. Voyager 2 carried a working plasma science instrument that Voyager 1 did not, providing first-of-its-kind observations of the nature of this gateway into interstellar space. That meant for the very first time, humanity had real direct measurements from the boundary between our solar system and the rest of the galaxy. And what those measurements showed stopped scientists cold. The first measurements surprised researchers. Cosmic rays increased dramatically. The solar wind almost disappeared. Plasma became denser than many scientists expected. Perhaps most surprising of all, Voyager 2 found that the magnetic field beyond the heliopause remained closely aligned with the field inside the solar system, challenging several expectations about how this invisible boundary would behave. Read that again. The magnetic field beyond the edge of the solar system was aligned with the field inside it. That should not be the case. The interstellar medium, the vast space between stars, was supposed to have its own magnetic field orientation, independent of our sun's influence. The models predicted a sharp, clean boundary where our solar magnetic field would end and something foreign would begin. Instead, what Voyager 2 found looked almost like a continuation, like the universe outside our solar bubble is somehow connected to the universe inside it in ways we did not fully account for. But here's where it gets worse, because that anomaly was just the beginning. Both Voyager spacecraft detected a searing hot region of space where the sun's influence ends and interstellar space begins. The probes identified this boundary zone at the edge of the heliosphere where temperatures spiked to an estimated 30,000 to 50,000 Kelvin. The region lies beyond the orbit of Pluto, in a transitional zone called the Helios Heath, where the solar wind slows and interacts with the interstellar medium, 50,000 Kelvin. To put that into perspective, the surface of the sun burns at approximately 5,778 Kelvin. What Voyager 2 encountered at the outer edge of our solar system was a wall of heat nearly 10 times hotter than the surface of the star it had been fleeing for over 40 years. Nobody predicted this. Nobody modeled it. scientists are still debating what generates temperatures that extreme at the boundary of our heliosphere. And this is not a minor footnote in a scientific paper. This is a fundamental mystery about the nature of the environment our entire solar system exists within. In addition to the temperature rise, both Voyager spacecraft provided magnetic field data that surprised scientists. Magnetic field lines inside the heliosphere were found to align with those in the region just outside. And then, on top of that, Voyager 2 recorded that the solar magnetic field tied to the solar wind drapes around the heliopause, and that the interstellar magnetic field outside is oriented differently, creating a more complex interface than expected. Complex is the scientific way of saying, we do not fully understand this. The boundary of our solar system is not the clean, predictable line that textbooks described. It is layered, dynamic, and behaving in ways that our models are still struggling to explain. Think about what that means. We have spent decades building theoretical frameworks for the structure of our solar system's outer boundary. We sent probes to test those frameworks. And the probes came back, metaphorically speaking, and told us that significant portions of what we thought we knew were wrong, or at best, deeply incomplete. And this is where everything changes. Because Voyager 2's final images, its final transmissions from its cameras before those imaging systems were permanently shut down, told a different kind of story. One that was not about data points and magnetic field measurements. One that was about the sheer scale of human smallness against the backdrop of interstellar space. The photos taken by NASA's Deep Space Network are hazy and speckled, distant stars just visible in the inky blackness of interstellar space. But their scientific and emotional impact is profound. These last images provide a ghostly illustration of just how far Voyager 2 has gone and the unimaginable distances it has traveled between Earth and the stars. These were not the sharp, vivid images that Voyager 2 transmitted during its planetary flybys decades ago. These were the images of a machine at the absolute limit of its capabilities, in a place where no light from nearby stars could illuminate anything, capturing the darkness between worlds. And somehow, that darkness was more powerful than any photograph of Jupiter's storm systems or Saturn's rings had ever been. Because what those final images communicated, and what Voyager 2's entire interstellar mission ultimately communicated, was this: we are not in an empty universe. We are in a structured one. One with boundaries and temperatures and magnetic alignments and plasma densities that we did not expect and do not fully understand. And we are only just beginning to explore it. Now let us go back further, because Voyager 2's story did not begin at the edge of the solar system. It began with a grand tour, a rare alignment of the outer planets that occurs only once every 175 years, and which allowed a single spacecraft to use gravitational slingshots to visit Jupiter, Saturn, Uranus, and Neptune in a single extended mission. NASA recognized this window, and they launched Voyager 2 to take full advantage of it. Voyager 2 is the only spacecraft to study all 4 of the solar system's giant planets at close range. It discovered a 14th moon at Jupiter, was the first human-made object to fly past Uranus, discovered 10 new moons and 2 new rings at Uranus, was the first human-made object to fly by Neptune, and at Neptune discovered 5 moons, 4 rings, and a great dark spot. That list reads like a highlight reel of discovery. But each of those bullet points contains within it decades of follow-on research, debates, and revelations that continue to this day. Take Europa, Jupiter's ice-covered moon. Voyager 2 photographed Jupiter's moon, Europa, showing a smoother surface than on other icy moons. Researchers noticed dark bands crisscrossing Europa's surface like cracks that have been filled, suggesting icy material may have flowed into those cracks. At the time, this was an intriguing observation. Today, it is the foundation of one of the most significant scientific questions of our era. Does Europa's subsurface ocean harbor life? A mission to answer that very question, the Europa Clipper, launched in October 2024, carrying the legacy of Voyager 2's 1979 flyby into the next chapter of exploration. And then there is Triton, Neptune's moon. Unlike most moons, Triton orbits Neptune in the opposite direction to the planet's rotation, suggesting it was once a captured object from the Kuiper Belt. Voyager 2's images revealed geysers of nitrogen erupting from its icy surface, evidence of active geology on a frozen world. These discoveries change scientific perspectives on moons as dynamic and diverse bodies, not just passive companions to their planets. Before Voyager 2, a moon was a rock, a companion, a thing that orbited and did nothing particularly interesting. Voyager 2 obliterated that idea. Moons were worlds. Some of them were volcanic. Some of them had atmospheres. Some of them had liquid oceans beneath their surfaces. Some of them might even have the chemical preconditions for biology. That is what a single spacecraft, running on 47-year-old technology, gave us. Not just data. A complete reorientation of how we think about the potential for life beyond Earth. But now, in 2025, the story has entered its final act. And this is the part that most people are not paying attention to. Because right now, in real time, Voyager 2 is going dark. Instrument by instrument, system by system. The engineers at NASA's Jet Propulsion Laboratory are engaged in a slow, deliberate process of managing the spacecraft's diminishing power, making agonizing choices about what to keep alive and what to let go. Launched in 1977, Voyagers 1 and 2 rely on a radioisotope power system that generates electricity from the heat of decaying plutonium. Both lose about 4 watts of power each year, 4 watts per year. That is almost nothing. But over nearly 5 decades, it has accumulated into a critical shortage. Mission engineers have taken steps to avoid turning off science instruments for as long as possible because the science data collected by the twin Voyager probes is unique. There is no replacement for this data. Voyager 2 is in a place no other active spacecraft has ever been. Everything it measures alone. Mission engineers at NASA's Jet Propulsion Laboratory turned off the cosmic ray subsystem experiment aboard Voyager 1 on February 25, 2025, and shut off Voyager 2's low-energy charged particle instrument on March 24, 2025. 3 science instruments will continue to operate on each spacecraft. And then came the sobering statement from Suzanne Dodd, the Voyager project manager at JPL. The Voyagers have been deep space rock stars since launch, and we want to keep it that way as long as possible. But electrical power is running low. If we don't turn off an instrument on each Voyager now, they would probably have only a few more months of power before we would need to declare end of mission. End of mission. Read those 3 words and let them sit for a moment. End of mission. The longest running mission in the history of space exploration. A mission that has been operating since Jimmy Carter was president of the United States. A mission that has outlasted the Cold War, the fall of the Berlin Wall, the rise of the internet, the birth of the smartphone, and nearly half a century of human civilization. End of mission. With the latest instrument deactivations, the mission is expected to continue for at least another year before further power reductions require additional shutdowns. Voyager 2 will continue running its magnetic field and plasma wave instruments, with its cosmic ray subsystem planned for shutdown in 2026. These power-saving measures are expected to allow the spacecraft to continue functioning with at least 1 active science instrument into the 2030s. Into the 2030s, with 1 instrument. This is what the end looks like for the greatest explorer humanity has ever built. Not a dramatic explosion, not a failed signal, just a slow, careful dimming, like a campfire that has burned through the night and is now settling into its last glowing embers at dawn. But here is what mainstream coverage keeps missing. The significance of what Voyager 2 is still doing right now, in its final operational years, is not less important than what it did during its planetary flybys. In some ways, it is more important. Because the data it is gathering about interstellar space, about magnetic fields, about plasma density, about cosmic ray behavior beyond the heliopause, is the only such data in existence. There is no other active spacecraft in interstellar space that can supplement or verify it. Voyager 1 exited near the heliosphere's leading edge, where it collides with the interstellar medium, and Voyager 2 exited along its left flank. They took different paths. They measured different things, and together they constitute a 2-point sample of an environment that spans an essentially infinite canvas. Think about what that means for science. Cosmologists and heliophysicists are trying to understand the structure of the heliosphere, the shape of the bubble our sun creates around itself, using data from exactly 2 spacecraft at exactly 2 exit points, gathered over a span of decades. Research published in early 2024 suggests the heliopause may be shaped differently than once believed. Instead of a thin boundary line as once thought, this new work suggests a thick boundary layer. Such a layer may form where magnetic fields from the heliosphere and interstellar space interact. A thick boundary layer, not a sharp edge, not a clean line of demarcation between our solar wind and the interstellar medium. Something more like a transition zone, deep, complex, possibly hundreds of millions of miles wide, where 2 fundamentally different cosmic environments gradually blend into each other. The big surprise was that the 2 probes encountered the heliopause at about the same distance from the Sun, even though one occurred at high solar activity and the other at low activity. Scientists expected that the edge of the heliosphere could move as the Sun's activity changes. We don't understand why that is. That last sentence, understated, academic, scientific in tone, is actually a confession. A confession that one of the most fundamental assumptions built into our models of the solar system was wrong. Or at minimum, that something is happening at the edge of our heliosphere that our physics has not yet accounted for. And in 2024, scientists went back even further. They re-examined Voyager 2's old data from its 1986 flyby of Uranus, data that had been sitting in archives for nearly 4 decades, and found something they had missed. In 2024, researchers revisited 38 Year-old Voyager 2 data had identified a critical solar wind event that compressed Uranus's magnetosphere just before the flyby, an event occurring only about 4% of the time. 4% of the time. Voyager 2 happened to arrive at Uranus during one of the rarest windows in that planet's magnetic cycle, which means everything we thought we knew about Uranus's magnetosphere, an entire planetary characteristic, was based on a snapshot taken during an extreme anomaly. The Uranus we studied from Voyager 2's data was not the typical Uranus. It was Uranus in crisis. And we did not know that for nearly 40 years. This is what informed sources in the planetary science community are quietly acknowledging, that the Voyager 2 dataset, even decades after collection, continues to overturn assumptions. The spacecraft is physically dimming, its power is fading. But its legacy is, in a very real sense, expanding, because modern artificial intelligence and advanced image processing are unlocking details in Voyager 2's archived data that the hardware of the 1980s could never have extracted. NASA is now investing in artificial intelligence foundation models, open-source AI tools designed to extract new findings from existing science data, to further leverage its vast archives. Which means Voyager 2 will continue to make discoveries long after the last instrument aboard it goes dark. The data already exists. The tools to read it more deeply are only now being built. What most people are not seeing is that this is not simply the end of a spacecraft. It is the beginning of a new phase of discovery. One where the spacecraft itself is silent, but the information it gathered continues to speak. The measurements are stored. The images are archived. The magnetic field readings, the plasma density numbers, the particle flux data, all of it sits in databases at JPL and in research institutions around the world, waiting for the next generation of analytical tools to squeeze new truths from them. But let us be honest about something. There's also genuine loss here, not just scientific loss, but something more difficult to quantify. The Voyager program represents a kind of ambition that is increasingly rare in institutional science, a willingness to commit to a mission with a timeline, measured not in years, but in generations. The scientists who built Voyager 2, who designed its instruments, who plotted its trajectory, who celebrated its planetary flybys, most of them are no longer with us. And the scientists who are now managing the end of the mission have spent their entire professional careers working on a spacecraft that was launched before many of them were born. This is not just a technical milestone, it's a deeply human one, said Dr. Suzanne Dodd, Voyager project manager at NASA's Jet Propulsion Laboratory. We're watching the slow farewell of a spacecraft that has taught us more about our place in the universe than almost anything else. There is something in that statement that goes beyond professional pride. It is grief, a specific kind of grief that comes from watching something irreplaceable approach its end. Because there is no Voyager 3. There is no mission currently planned to replace what Voyager 2 does in interstellar space. NASA's New Horizons spacecraft is zooming out of the solar system at more than 31,000 miles an hour. And when it runs out of power in the 2030s, it will fall silent more than 1 billion miles short of the heliosphere's outer edge. 1 billion miles short. New Horizons, the spacecraft that gave us our first detailed images of Pluto, will not even reach the boundary that Voyager 2 crossed 6 years ago before it, too, falls silent. There is a proposed interstellar probe, a 50-year, multi-generation mission that would explore the outer solar system on its way into unexplored regions beyond the solar wind. 50 years. Multi-generational. That is the kind of commitment required to do what Voyager 2 did. And that mission has not yet received full funding authorization, which means that when Voyager 2's final instrument goes dark, whether that happens in the late 2020s or sometime in the 2030s, there will likely be a gap, a silence, a period when humanity has no active presence in interstellar space, no ears beyond the heliosphere, no instruments measuring the true nature of the environment our solar system exists within. The real story is this. We are at a pivot point. Voyager 2 is ending. The replacement has not yet been launched. And the universe beyond our solar system, the one that does not behave the way we expected, the one with a 50,000 Kelvin heat wall and the misaligned magnetic fields and the thick, mysterious boundary layer, is not going to stop being mysterious just because we stop looking at it. By 2025, both Voyagers lose about 4 watts of power each year, which necessitates turning off even some formerly critical instruments to keep the remaining ones functioning. The math is brutal and inexorable. Every year there is less power. Every year another instrument falls silent. The spacecraft do not malfunction. They do not crash. They simply run out of energy in the cold dark between the stars, still pointing their antennas back toward a pale blue dot they left behind nearly 5 decades ago. And here's the question that nobody in the press conferences wants to sit with for too long. But what else is out there? What other anomalies? What other impossible heat walls? What other magnetic mysteries are waiting beyond the small patch of interstellar space that Voyager 1 and Voyager 2 have sampled? The two spacecraft exited the heliosphere in different directions, at different times, under different solar conditions, and still found behavior that contradicted our models. What does that suggest about the rest of the boundary, the parts we have never sampled? What might we find in the direction the heliosphere is moving through the galaxy? What is in the heliospheric tail, the region behind us in our galactic orbit, where the boundary extends in ways we have never directly measured? There is still a lot to learn about the region of interstellar space immediately beyond the heliopause, said Ed Stone, Voyager project scientist based at Caltech. That statement was made years ago, and every piece of data that has come back since then has confirmed it. The learning has not slowed down. If anything, each new analysis opens more questions than it closes. This is the hidden architecture of great discovery. You set out to confirm what you know. You find, instead, that what you thought you knew was only the outline of a much larger, stranger picture. Voyager 2 was built to map the outer planets. It did that. And then it kept going. And in the going, it found that the edge of our solar system is not a wall, but a conversation. A dynamic, churning, thermodynamically violent negotiation between our sun's magnetic domain and the broader galaxy beyond it. There is something philosophically profound in that. The idea that our solar system does not have clean edges, that the sun's influence does not simply stop and give way to something else, that there is a zone of mixing, of interaction, of competing forces, thick and complex and not yet fully understood, between where we live and where the rest of the galaxy begins. It makes the universe feel simultaneously larger and more intimate, like the boundary between home and the wilderness is not a door, but a gradient. As Voyager 2's power continues to decline through 2025 and beyond, the scientists watching over it are making increasingly difficult choices. Voyager 2 will continue to operate its magnetic field and plasma wave instruments for the foreseeable future. Its cosmic ray subsystem is scheduled to be shut off in 2026. The magnetometer will stay on as long as possible. It is arguably the most valuable remaining instrument because magnetic field data from interstellar space is irreplaceable. Every reading it returns is a data point in a data set that will never be repeated. And then, at some point, perhaps in 2029, perhaps in 2031, perhaps sooner if something unexpected fails, the last signal will come. It will not announce itself as the last signal. It will arrive at the deep space network antennas, be processed, be added to the database, and then the next scheduled contact will yield nothing. Silence. Not because something went wrong, because the physics ran out. Because a machine launched almost 50 years ago, running on plutonium and human ingenuity, finally exhausted the last of what it had to give. What did Voyager 2 find? It found that Jupiter's moons are worlds in their own right. It found that Neptune is colder and stranger than we imagined. It found that Triton erupts. It found that Europa might be alive. It found that the edge of our solar system is not where we thought it was and does not behave the way we thought it should. It found a wall of impossible heat at the boundary of everything. It found magnetic alignments that defied prediction. It found that interstellar space is not empty but textured, filled with plasma and cosmic rays and forces that interact with our sun in ways that are still, after decades of study, not fully understood. But perhaps most importantly, and this is what gets lost in the coverage, Voyager 2 found that we know far less than we think we do. That our models, our theories, our confident predictions about the nature of our own solar neighborhood were repeatedly and sometimes dramatically incorrect. And that the most important thing we can do is keep building the instruments, keep launching the missions, keep listening, because out there, beyond the heliopause, beyond the thick and churning boundary layer, beyond the heat wall and the misaligned magnetic fields, the galaxy is doing something. And we are only beginning to hear it. The spacecraft is dimming, the mission is ending, and the universe is not waiting for us to figure it out. What happens when the last signal goes quiet? What are we missing right now in real time? Because we have not yet built the successor. And if the boundary of our solar system is this strange, this complex, this hot, this magnetically surprising, what does that tell us about every other star system in the galaxy and the bubbles they create around themselves and what might exist inside those bubbles? The answers are not in yet, and the machine that was closest to finding them is going dark.